one thing you can do is the alkyl side chains on a benzene ring are a little bit more reactive than they otherwise would be. So you can actually convert them into important functional groups like a carboxyl group through oxidation. Okay, so in the presence of an aromatic ring, alkyl side chains are converted to carboxyl groups through oxidation. All right, you're given the example here. So something to point out is it doesn't matter how long the chain is. It could be, in this case, it's 4 carbons, but it could be 1 carbon, it could be 3 carbons. It really doesn't matter how long the chain is, but what you get is the same product because the reactive part is right there. It's the, it's this benzyl part. This is the reactive part. And so you can convert those into carboxyl compounds, and in particular, it starts with benzoic acid. You can take it from there and convert it into other carboxyl type compounds. But you start by converting it into a carboxylic acid with the potassium permanganate in water. Now, I kind of pick and choose which mechanisms that I want you to learn. This one definitely not, because I'm not sure how well even organic chemists understand it. It's a complex mechanism, which means they don't quite understand it either. But it has to do, as I said, with that benzylic position, that carbon that's directly attached to the benzene ring. And if there are hydrogens on it, then those hydrogens are particularly reactive because the benzyl radical has added stability. So this involves a complex mechanism where the CH bonds next to the aromatic ring react to form intermediate benzylic radicals. So if you don't remember what that means, the benzylic radicals, it's this right here where, it's kind of like allylic, where it's on a carbon that's not engaged in a double bond, but it's on a carbon that's next to a double bond. And in this case, it's next to a series of double bonds, that pattern of double bond, single bond, double bond. It's like allylic on steroids, right? Because that, you can follow the reaction, the electron pushing arrows, the reaction arrows there, the curved arrows, I should say. And that radical, that free electron, that unpaired electron, I should say free electron, that unpaired electron, moves around the ring. So it can go from the carbon in the benzylic position to 3 different places on the ring. So anytime you have that, it delocalizes it, makes it more stable, and it really is the fundamental explanation for why this reaction occurs, because of the stability of that radical. Okay? But something else that we have looked at before, and we're just going to talk about it again, is that you have this special reactant that can put a bromine in place of a hydrogen in an allylic or benzylic position. And that reactant we've already talked about, it's NBS, N-bromosuccinimide. So hydrogen in the benzylic position can be substituted with bromine by NBS. And so once again, you don't need to know the mechanism, you just need to know what the product would be, the transformation would be. So you have a hydrogen in a benzylic position. Okay, so either one of these hydrogens, the way they have written it out, it's that one. And it just gets substituted with the bromine from the N-bromosuccinimide. And so this is not even related to the oxidation reaction we showed in the previous slide. It's just further evidence that the mechanism that that the alkyl side chain undergoes is because of this benzylic position, is like the starting point, okay, to transform that alkyl group. Because the same thing kind of happens here. It gets transformed. In this case, it's less of a transformation. Instead of lopping most of it off and converting the benzene into the alkyl benzene into benzoic acid, it just transforms that alkyl chain at the benzylic position to take on a halogen. All right, so let's just practice this a little bit. This is just, we want to prepare styrene from benzene using what we just talked about. Let's think about a way where perhaps we could prepare styrene, and you've got the structure for styrene right there. We're going to start with benzene, so let me draw that. You got your stencil with you. That might be nice. So that's the starting material, and I want to go to styrene. Okay. Well, what if I do some sort of Friedel-Crafts reaction? Remember, we can do that with an alkyl halide, and so in this case, if I just have 2 carbons, right? I'm trying to add 2 carbons to it. So one thing that we want to do is we want to do a Friedel-Crafts reaction where, remember, we can use an alkyl halide. In this case, it's a 2 carbon with the chlorine and the aluminum chloride. Okay. So then we just talked about, well, we could use this reactant called N-bromosuccinimide, and so it's going to change out that benzylic position with a bromine. So right here, it's going to, or here, they're equivalent. Okay. But the key is that's going to get changed into a bromine. So now I've got the benzene ring where that carbon has one hydrogen, but now it's also got a bromine, okay, Br, and then this carbon still has 3 hydrogens on it. And so then we also talked about a reaction. This is a little bit of review, again, trying to get some review in where I can this week. So if we do this with a strong base, we subject this to something like KOH, a strong base, okay? You get either, it could be an E1, it could be an E2, we're not exactly sure of the mechanism, but you get an elimination reaction, okay? So the idea here is we're gonna cause an elimination. Okay, so let me change colors to illustrate what happens. So the electrons on the OH minus is going to grab that hydrogen, so it's going to dump its electrons between those 2 carbons, and then the bromine is going to act like a leaving group. Remember, that's what happens with an elimination. Okay, and so then the product is going to be what we want, styrene. Because now we've got a double bond. So now we've got a carbon with 1 hydrogen, and it's got a double bond with the other carbon. Okay, and that base took on that hydrogen, so the byproduct is going to be a water molecule. Okay, but then you form the alkene through the elimination reaction. So another reaction that we want to talk about with regard to aromatic compounds is reducing it. You got all those double bonds in that benzene ring. Can we add hydrogen into it to just reduce it down to the alkane? Well, turns out that that's pretty difficult. Aromatic rings are inert to catalytic hydrogenation under conditions that reduce alkene double bonds. So we can take advantage of that, though. If we want to reduce a double bond in a compound without affecting in any way the aromatic part of the compound, we can do that. One can selectively reduce an alkene double bond in the presence of an aromatic ring. So, for example, the reaction that you have in your notes there, we've got double bonds all over the place in 4-phenyl-3-butene-2-one, right? Technically there's 4 of them, but we know that in a benzene ring, those electrons are really delocalized, and it's just one way of representing the benzene ring is with alternating double bond, single bond, double bond, single bond, and it does react that way sometimes, but nonetheless. So you might remember from our discussions earlier this semester about using hydrogen on a palladium catalyst, okay, to reduce an alkene, and that's what you can do without affecting the benzene ring at all. So we selectively reduce that alkene functional group while leaving the aromatic functional group alone. That's what you're supposed to get from this. Okay, so how do you, if you really did want to reduce the aromatic compound to a cyclohexane, just an alkane, how do you do it? Well, you could do it with a platinum catalyst, but it also requires very, very high pressures. Pressures over 100 atmospheres of hydrogen. Okay? Or you could use a specialized catalyst, which instead of platinum or palladium is going to be rhodium, Rh. So that's in the same area of the periodic table. If you look at the periodic table, there's rhodium. It's near platinum, palladium. So these are the normal catalysts we would use for hydrogenation, palladium and platinum. So it's in the same neighborhood, but it's just more effective for this particular purpose. Okay, so the way you could do it, if you want to go from an aromatic compound to just a cyclohexane, you could do it with a platinum catalyst, but you got to have a really high pressure of hydrogen, 130 atmospheres in this case. Or you could use a specialized catalyst of rhodium plated onto carbon, and it's just normal type pressures. So you could also just exploit this to reduce a carbonyl. Okay, so for example, if you wanted to make propylbenzene, the way you'd actually need to do it is you would first of all do a Friedel-Crafts reaction, as you can see from this reaction scheme. Well, I guess we'll write down the text first in the bullet, and then we'll talk about the reaction. So an aromatic ring can activate neighboring carbonyl group towards reduction. So just like it activated that benzylic position for substitution or free radical formation, it also can activate a carbonyl. And it makes it more likely to be reduced with normal reducing conditions like what we've seen with alkenes, just the hydrogen on a palladium catalyst. Okay, so it just adds those hydrogens to the carbon. You notice that the oxygen is gone. You eliminate water as a molecule. But what was a carbonyl just gets reduced down to a CH2. So that's the big transformation to recognize. You go from a C double bond O to just a CH2 group. Okay? And it's because that benzene ring just activates that carbonyl, makes it more reactive for reduction. Okay, and as I was saying before, I got sidetracked, is you would want to do it this way because, and this is another review topic, of the possibility for rearrangement. Okay, so let me show you what that is. Okay, and you got this already in your notes, I believe. But if you just do a normal Friedel-Crafts reaction with a propyl chloride, one chloropropane, I guess is the IUPAC name for it, 1-chloropropane, you could get that rearrangement, which is going to give you a mixture. So you could get some propylbenzene, but also you're going to get isopropylbenzene. So remember the mechanism of how that can happen. So this, if I redraw this, we got CH3. Okay, so let's just do it with all the hydrogens shown. CH3, so CH3, and the CH2, and then another C, H. And now let's say that the chlorine is already left. So there's like a carbocation, okay, in this reaction. So the benzene acts like the nucleophile, and that carbon right there is going to be the source of the electrophile. Okay, so remember that this is a primary carbocation. Okay, well, if one of these hydrogens just moves over, if it rearranges, that, like for example, that hydrogen moves over, then it becomes a secondary carbocation, and that's how you get the isopropyl product. And that can happen and does happen. You get that hydride shift. Okay, so this was, remember we called that a hydride shift. Okay, so I just as a reminder, we'll look at some more review situations of this in the next couple of days, that in organic 2, I do expect you to know how a hydride shift can occur or an alkyl shift can occur, but I'll always give you a hint when, I'll say, you do need to consider rearrangements. It doesn't mean it's going to happen every time, but, in this course, I do want you to account for those hydride shifts or methyl shifts in what product might be formed. So, example problem here. We want to prepare diphenylmethane. That's just, instead of CH4, 2 of the hydrogens have been replaced with benzene rings, phenyl groups, from benzene and an acid chloride. So we want to think about the right way to prepare that. Well, once again, if I do this reaction, okay, in the presence of aluminum chloride, okay, I get a Friedel-Crafts reaction that's just going to substitute one of the hydrogens on this benzene ring with this part of the molecule. So the intermediate product is going to be benzene ring, then the carbonyl, so C double bond O, which is just going to be attached to the other benzene ring. So they just did a substitution. Ugh, that is a really bad benzene ring. Sorry. So just do the substitution where, in this case, this hydrogen gets substituted with that acyl group. Okay? But I'm not done, because what I ultimately want is diphenylmethane. So I need to reduce. Okay? So I need to reduce this. And you can just do that with your typical reducing conditions, H2 over like a palladium catalyst, maybe palladium carbon particles have been coated with palladium metal, something like that. And it just, reduces it down to, I'm just going to abbreviate here, phenyl. Remember, phenyl is just the way you consider a benzene ring if it's a substituent rather than if you're thinking of it as a substituent. So we just do a Friedel-Crafts reaction to get this intermediate compound, and then we just use reducing conditions, and it works because both of these, in this case, both of these benzene rings are going to activate that carbonyl for reduction, and you end up with the desired product.